In this video, we solve problem 8.2.508.xp.mi from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the integral or evaluate the integral. Kind of hate the word find the integral. I'm like, it's right here. But we're in the integration by parts section. So we pretty much know we're going to do integration by parts with this. But I've had many students try this and say, oh my goodness, whenever I do this, it seems like the sine and cosine just keeps going back and forth and I don't know what to do. And I wanted to show you exactly how to handle this. So we want to use integration by parts for this because U substitution won't work. It's not a basic rule because you've got a product of functions. Now you can let U equal this exponential function or this cosine function. Either one is going to work just fine. I tend to let U equal the exponential in this case. It actually works just as easily the other way. So we'll let U equal e to the 3x. And then remember, everything else is dv when you're doing integration by parts. And remember, generally you want to choose the function with the simpler derivative to be U. It's hard to say whether e to the 3x or a sine of 4x is simpler. So we're just going to choose U to be this and dv to be this. But regardless of what you choose, you have to choose with a couple of restrictions in mind. You need to be able to compute du, which we can do with all the functions that we're familiar with. And we also need to be able to compute v, so we need to be able to anti-differentiate this. Since we can anti-differentiate this, and obviously we can differentiate that, we can do this. We can proceed with this choice. So we differentiate to find du, and then we're going to anti-differentiate to find v, or to compute v. The derivative of e to the 3x is e to the 3x times the derivative of the inside by the chain rule. That's a 3 dx. That's a 3, and then the dx comes from the differential. And then the dv, if I want to go from here to here, I had to differentiate this way. I'm anti-differentiating that way. The antiderivative of cosine is sine. And if you've got a constant times x inside, if we were taking the derivative, we'd have to multiply by that constant. To take the antiderivative, we have to divide by that constant. Now, according to the integration by parts formula, which we derived in other videos, the integral of u dv is uv minus the integral of v du. So if you set up your 2x2 table this way every time, you'll multiply across the top. That's going to give you u times v. And then you'll subtract the integral of v du. So we've got e to the 3x times cosine of 4x. The antiderivative of that is equal to this, u times v. That's 1/4 e to the 3x times sine of 4x minus the integral of v times du. That 3 times that 1/4 will give me a 3/4. And then I've got an e to the 3x there and a sine of 4x right there. And then you look at that and you say, do I have a basic rule for that? And we don't. And then you say, can I use U substitution for that? Well, not really. It's pretty much the same difficulty level as that one was. So we're just going to end up using integration by parts again. So what I would recommend is that you take out that 3/4, factor that out, and then use integration by parts again. I'll still use u, or the exponential as my u, and dv is everything else. So u is e to the 3x, dv is sine of 4x dx. Then we differentiate to get u, and we anti-differentiate to get v. The derivative of e to the 3x is e to the 3x times the derivative of the inside, that's a 3, times dx for the differential. And the antiderivative of sine is negative cosine of the same angle If we were taking the derivative, we'd multiply by 4. When we're taking the antiderivative, to undo that, we divide by 4. And once again, you're going to have the antiderivative of u times dv is uv minus the integral of v du. So we've got 1/4 e to the 3x sine of 4x minus 3/4. And be careful here, you need parentheses there because that negative 3/4 multiplies the whole result from that integral, and the whole result has 2 terms. So if u times v, it's minus 1/4 e to the 3x times cosine of 3x, or cosine of 4x, excuse me, minus the integral of v times du. We're subtracting a negative, so that's going to be adding 3/4 e to the 3x times cosine of 4x dx. Now I might distribute that negative 3/4 next. That negative times that negative would make that a positive 3/16. And that negative 3/4 times this positive 3/4 is going to give me a negative 9/16. Okay, and this is where students start to worry because they say, I have an e to the 3x cosine of 4x over here, and didn't I have one of those to start with? Am I not just going to keep repeating this pattern over and over? And the truth is, we could do that, and we'd be here a long time. We'd be here forever. But there's an easier way. I know it looks like alphabet soup. It looks like this is impossible to solve at this point, but we're actually really close to getting the answer because all of this over here is still equal to that. I didn't bring that down every time, but I could have. So let's just write that down here. And remember what our goal is. Our goal is to find this guy. We want to get him by himself. We want to know what the antiderivative of e to the 3x times cosine of 4x is. Well, when I see him again over here, I might worry because maybe we did integration by parts in such a way that all these terms cancel and we get the integral is equal to itself. And sometimes that does happen, and we say, okay, we've got to try something else. But that's actually not what happened here. I've got the quantity I'm looking for on this side and the quantity I'm looking for on this side, but it has a negative coefficient in front. Solving this is very similar to solving something like this. Like if I've got x equals 5 minus 2x. The thing I'm looking for is over here, and then negative 2 times what I'm looking for is also on the other side. And we've got all this other stuff. That's just like the 5. But if I want to get x by itself, all I would have to do is add this to both sides so that I would get 3x, and then divide by 3 to get x by itself. So we're going to do the same thing. I've got negative 9/16 of what I'm looking for over here, and then I've got one of those over here, so I'm going to add that to both sides. And it's not just 9/16, it's 9/16 of that entire integral. And so this is how you want to think about it. If you take that and you add that, that will undo that, and those guys are gone. And then over here, you had one of these, which is 16/16 of these. And now you're adding 9/16 of those. So now we've got 25/16 of those. And it's an indefinite integral, so we should really add c eventually. It should be, that x should be up there in the exponent, sorry. And I'm trying to get this exponential by itself. Well, to do that, all I have to do is multiply by the reciprocal of this coefficient, that would just give me a coefficient of 1, because that's what I'm looking for. I'm just trying to get one of these, not 25/16 of these. So I will multiply this guy by 16/25, which is legal as long as I multiply everything over here by 16/25. So multiply that one by 16/25, and then multiply this term by 16/25. Then let's add a c for the constant of integration. And then we end up with this. The integral of e to the 3x times cosine of 4x is equal to this. The 4 goes into 16 4 times, and we have 4/25 times that exponential times sine. And it turns out we've got 3/25 times the exponential times cosine plus c. Now, sometimes it's hard to believe, but just due to the nature of sines and cosines and the fact that the derivative of sine is cosine and the derivative of cosine is a negative sine, if we use the product rule to take the derivative of this, and we use the product rule to take the derivative of this, we're going to end up with exponentials times sines and exponentials times cosines. And some of them are going to have opposite SIGN signs, so they're going to cancel. We take the derivative of this using the product rule and the derivative of this using the product rule and add those results together, I claim that you get this over here. Should we verify it? Nah, I'm not going to verify it this time. But if you want me to verify it, I will. Just let me know. You should check it out for yourself, though. If you don't believe this is true, take the derivative of this and you should get this. If the derivative of all of this is equal to that, then you know that you've successfully taken the antiderivative correctly.